This is the first lecture in the Moon 101 series, and it's designed to give you a brief overview of a lot of different subjects about the moon that other lecturers will go into in more detail in the successive lectures. My name is Dean Epler. I'm a retired NASA lunar geologist, and I'm presenting this material, although it was originally put together by Paul Spudis, the scientist who originated the whole Moon 101 concept about 10 years ago. Paul has passed away, and I'm trying to fill in for him, hopefully in such a way that he will not be disappointed. So the first important part that we need to discuss is really what the moon is. And the real key, I think, is that the moon is a planet. It has many of the features that we think of as a planet, as in having a core, having a mantle, having a crust. No other planet is as proportionally large as the moon is with respect to the size of the Earth. Many of the other planetary bodies that have moons, such as Mars, have small irregular moons that seem to be just sort of, accidentally captured into the orbit of their primary body. The moon has a heavily cratered surface. It is partially flooded by lava flows, which erupted somewhere between 4 billion and about 1 billion years ago, with the bulk of the lava being emplaced around 4 to 2.2 billion years ago. Since the moon has formed, there have been many impacts by comets and asteroids, and they have radically altered the outer surface of the moon. It has created what is a chaotic upper layer of debris, which we call regolith, and it has deeply fractured the lunar crust to a depth of over 10 kilometers. By and large, the moon was a dead planet by about 1 billion years ago. There's a lot we don't know about the history of the moon, and some of these unknown items are key to understanding the history of the Earth-Moon system. The moon is covered by a particulate blanket, and I say particulate blanket because it is really a mix of particle sizes all the way from extremely tiny sizes all the way up to boulders that are the size of a building. It is easily accessed. It is a likely feedstock for resource extraction. And if you look at the picture of John Young's feet, this picture was taken on Apollo 16, you'll see that there is actually fluffy dirt regolith kicked up around it. And it gives you a nature of how loose and fluffy the upper layer of the regolith is. But in the upper right corner, you see the picture of an extremely small, but nevertheless almost perfect crystal of a mineral. The moon's regolith is full of things like this. As I said, it goes all the way from large rocks down to the finest fraction that you can imagine. I want to go into some general properties. On the left is the moon, in the center is Mars in red, and on the right is Earth in blue. And if you compare the numbers for any given variable across the graph, you're going to see that the moon and Mars are actually a lot more like each other than Mars is like the Earth. A lot of people have taken the view that Mars is more like the Earth, and to a certain extent, that's justified in light of what we think the early Martian history is now, in that we think it was warm and it was wet. But the size of the planet, its composition, its very nature makes it actually a lot more like the moon than it is like Earth. The moon has a history. Before Apollo, it was dubbed the Rosetta Stone of the planets. And after Apollo, in the immediate years after Apollo, a lot of people sort of wondered, well, was it really? But as time has gone on, and as we've analyzed lunar samples, we've come to believe that moniker, in fact, is absolutely correct. And much of what we understand now about the other planets in the solar system, as well as the Earth, we've learned because the moon has preserved a history that many other planets no longer have. Now, before we went to the moon on Apollo with human beings, we had quite a bit of precursor missions from the United States. In addition to that, the Soviet program landed a considerable number of spacecraft on the surface, as well as flew vehicles around it. Before we could even think about landing on the moon, we had to understand what the moon was actually like on its surface. And it's really important to recognize that before These vehicles went to the moon. The smallest thing we had ever seen on the lunar surface through terrestrial telescopes was about 1 kilometer on a side. And the questions we had before we sent these spacecraft there seem somewhat silly now, but there were things like, where do craters run out? Are the craters all the way down to the smallest size? Are there rocks on the surface? Is the surface capable of bearing the weight of a lunar module? All of these things now we understand, perfectly well. But before we went to the moon with people on Apollo, we didn't know any of that. And this set of robotic missions clarified that. And I'm going to talk about each one in turn. The first successful spacecraft that basically touched the moon was the Ranger series. The Ranger series were hard landers in that they had no other, I suppose you could say, objectives other than hitting the surface and imaging the surface all the way down. As such, the only thing they did was photograph the surface. But this was really key because prior to the Ranger set of missions, we simply had no idea what the surface was like at a human scale. Ranger answered a tremendous number of questions that, frankly, we had had since Galileo first turned his telescope to the moon. There was a whole variety of soft landers, which, for obvious reasons, did a lot more when they got to the surface than the Ranger did. The Surveyor was an American mission. It flew 7 total spacecraft in the series, of which I believe 4 were successful. The whole purpose of the Surveyor missions was to safely soft land on the moon, to understand the nature of the lunar surface, and to do some basic chemical analysis. But largely it was, you can think of it as largely a civil engineering mission. What we wanted to know is, A, can we land on the moon? Is it possible to have a spacecraft, fly to the lunar surface and survive? The second thing is, what is the surface like? Is it soft? Is it a hard rock? What is it like? Is it like a snowbank that will disappear into? And the Surveyor that we're still analyzing data from. The Soviets, in addition, flew 3 sample return missions to the moon in the 70s. The Luna 16, 20, and 24 missions not only brought back samples from places we did not go on Apollo, they did it robotically. And at this point, no other country on the Earth has robotically recovered a sample from the lunar surface. In addition, the Soviets landed 2 Lunokhod rovers, which were incredibly successful. They drove around the moon's surface, again in places that the Apollo missions hadn't gone. And the 2 sets of Soviet missions greatly enhanced what we understood from Apollo by simply providing complementary samples from other places on the moon the Apollo program did not get to. Lastly, Lunar Orbiter was another really key mission because it circled the moon and photographed about 75% of the surface. At that, up to the point of the Lunar Orbiter missions, the only real global view of the moon that we had was from telescopic observations, and telescopic observations that simply do not see the lunar far side. Lunar Orbiter was a mapping mission. It was intended to collect global mapping data that the Apollo program could use in planning landings. Now, recently, and I say recently within the last 10 years or so, we have been flying, not just we, the United States, but the human race has been flying a significant number of orbital missions around the moon. Countries that had never done this before, like China, Japan, India, have flown a number of really successful missions and again have enhanced our understanding of the moon's surface. In addition to that, the Chinese have landed a soft lander with a rover in a manner not dissimilar from the Lunokhod missions. Okay, the first mission I want to take a look at is Selene. This was flown by the Japanese Space Agency. It carried a variety of instruments on board with 3 general objectives. First was to photograph the surface. Before the Selene mission went, we did not have any better resolution of the surface than we had on Apollo. The Selene mission improved that considerably. In addition to that, it carried geochemical remote sensors, basically instruments that could look down at the surface and capture radiation that would tell us what the composition of the lunar surface was. And in addition to that, it carried instruments to look at the nature of space at the orbital altitude of the spacecraft. Chang'e 1 was a Chinese instrument and carried much or similar payloads and had similar goals to the Kaguya Selene mission. And it was doing essentially two big missions. One was to look at the lunar surface and to get good images and good altimetry. And the second was to collect remote sensing data on the composition of the surface as well. Chang'e 2 was similar to Chang'e 1, but it was primarily directed toward looking at the landing site for the Chang'e lander. So it was essentially a reconnaissance mission for a very specific spot on the lunar surface. Once it completed its mission, it left lunar orbit and went to the Earth Lagrange Point 2, and then went from there on an asteroid expedition. So it was an extremely capable spacecraft, and it is still flying. Chandrayaan was a mission that was flown by the Indian Space Agency, but included payloads not only from the Indian Space Agency, but from the United Kingdom, from ESA, and from the United States as well. Again, collecting more and more detailed information about the lunar surface, similar in a way to the other satellites. Now, the first one that I think is really critical from the United States is something called GRAIL, Gravity Recovery and Interior Laboratory Mission. GRAIL was a spacecraft, or actually a pair of spacecraft, whose mission was to map out the lunar gravity field in incredible detail. And the idea behind this spacecraft was that the two co-orbiting spacecraft could determine the difference between themselves to an accuracy of about 1 micron, or 1,000th of a meter. As that distance between the two spacecraft changed, that indicated that there was a change in the gravity field felt at orbit. And that in turn allowed us to do an incredibly detailed gravity map of the moon. Once it got its primary mission done at a particularly high altitude, they stepped the orbit down and got increasingly detailed data at lower and lower altitudes until, in fact, the spacecraft ran into the surface. Because the moon's gravity field is unusual, it's lumpy, we tend not to fly spacecraft close to the moon early on in a mission because it's very easy to have the spacecraft impact. So many spacecraft will be flown at a high altitude initially and then flown lower once we have a good data set. Another specific mission flown by the United States was a spacecraft called LADEE. Several times in the course of the Apollo program, we thought we may have seen particulate materials high in lunar orbit, and that remained a mystery as to what actually the high altitude environment was, particularly with respect to lunar dust. And the LADEE mission was flown to essentially look for lunar dust and to understand the nature of that high altitude environment. Lastly, and perhaps the most successful of all the missions, is the Lunar Reconnaissance Orbiter. Lunar Reconnaissance Orbiter was flown initially in the Constellation program, and essentially what it was doing was collecting all the data we felt we needed to plug holes in both the lunar map and our concept of global variations in things like topography and composition. LRO was originally planned to be a 1 to 2 mission. It is still in orbit. It's been there for 8 years, and it has returned some of the most phenomenally accurate and detailed photographs of the lunar surface that have ever been recovered. And they have changed many of the ways we think about the lunar surface. The only lander that has been on the surface since Apollo is the Chinese U-2 lander, which was carried to the surface as part of the Chang'e 3 spacecraft. It landed in Mare Imbrium, about 40 kilometers southwest from a crater called Laplace F, and it operated for approximately 2 lunar days on the surface. It was really important because it deployed to an area we did not go on Apollo, and in addition to that, it deployed instruments that we simply didn't even have during Apollo, such as a ground-penetrating radar. And it has returned data that is revolutionary, and it was a magnificent mission. So I want to talk about some gross properties of the moon. And it's always important to start with what the moon looks like, both from the Earth and that part which we mostly cannot see, and that's the lunar far side. The moon has presented a variable face to humankind. Specifically, it's got dark and light areas. And the variations in albedo, the reflected light, whether they're bright or dark, it turns out tell us some very important things about the moon that we now know because of the various spacecraft that have been there. This is a series of lunar globes that look at three different elements: thorium, titanium, and iron. And I want to look at these in great detail, but one of the things I need everybody to recognize from this is that the albedo, the change in the gray tone of the lunar surface, actually maps very nicely to composition. This is the iron map of a goodly portion of the moon, and the variations range from brighter, warmer colors as higher iron and cooler, darker colors as less iron. Now, if you look at the moon in plain light, like we see the moon when we look up at it, you can see that the higher, brighter colors on the iron map correspond to the darker areas on the moon. And that's because the darker areas on the moon are filled with lava flows, and lavas are basaltic in composition, the same kind of rocks you see in Hawaii, and they tend to be higher in iron than the lighter color rocks on the rest of the moon. So we can see from that composition reflects albedo. Now, if we look at the titanium map, we see something very similar, although there are some variations in this. Not all basalts are alike. Some basalts have higher titanium, some basalts have lower titanium. The color scheme is the same as the iron map. Brighter colors have higher, lower colors have lower titanium. And you can see that not all the dark areas of the moon, the lavas, have the same titanium composition. We essentially discovered that from Apollo, from return samples, and we were lucky before we even knew this that we picked sites that coincidentally turned out to be places that had variations in titanium. But again, you can see on the western side of the moon and on sort of the central eastern side, we have a lot of titanium, and much of the rest of the moon, we don't have much titanium. Lastly, if we look at thorium, we see, again, the darker areas of the moon having a lot of thorium, and thorium is a radioactive element, and it's indicative of sort of evolved magmas that have spent a lot more time cooking, and that will be discussed in a later lecture. But again, if you go back to the picture of the moon that we see from the Earth, you can see that the concentrations of thorium match many of the colors that we also see on the lunar surface. In this case, they map to some place that we call the Procellarum creep terrain, where creep, K-R-E-P, stands for potassium, rare earth elements, and phosphorus. Let's talk about the lunar surface environment, and there's really four parameters that I think are really important. One is temperature and sunlight. The two are paired, and the other two are hydrogen content and what you can see of the Earth and how easy it is to communicate. The temperature on the moon really divides the moon into two different regimes. One is polar, which are colder just like the Earth, and the other is the nonpolar environments, where depending on where the sun is, it'd be hot or cold, just like the Earth. At noon, we get the hottest temperatures. On the moon, at noon, we get the hottest temperatures. When the sun goes down on most of the moon, it gets quite cold at night. The poles, on the other hand, are colder, but the temperature is much more stable than it is on the rest of the moon. Let's talk a little bit about hydrogen content. Hydrogen is a really critical element for essentially living off the moon. You can combine it with oxygen to make water. You can use it as rocket fuel. So where the hydrogen is really important. The nonpolar portions of the moon, the hydrogen ranges from as low as 10 parts per million to as many as 90 parts per million. The poles, however, we're pretty sure that the hydrogen content on average is greater than 150 parts per million, and it's why the poles remain an attractive target for lunar settlement. Lastly, direct-to-Earth communications. The moon is in locked rotation with the Earth, and that means that basically wherever you are in the lunar near side, the Earth will be in sight and it'll always stay in the same place. At the poles, the Earth is really low to the horizon. If the terrain isn't in the way, you can see it all the time, much as you do from the front side. But there are many times when the terrain may block it. The lunar far side never sees the Earth. So if you're going to operate on the lunar far side and you want to talk to the Earth, you're going to need a continuous relay satellite. So let's talk in more detail about thermal conditions, because the temperature is what we're going to have to work in when we're on the lunar surface. Nighttime surfaces are very cold, down to as cold as 150 degrees centigrade. And noontime temperatures are equally high, about 100 degrees centigrade. Polar areas are either always dark or have grazing solar incidence. So there are areas that we refer to as the permanently shadowed areas. These areas are extremely cold. In fact, many people have estimated that these are the coldest places in the solar system. The permanently shadowed areas on the moon never see the sun and probably have not seen the sun for hundreds of millions of years. Consequently, they are extremely cold, down to 50 to 70 degrees Kelvin. Another critical part of the lunar environment is micrometeorites. First, there's no atmosphere to impede the impact of all debris, so the speed at which, or the velocity at which it's coming in from space around the moon is not attenuated at all as it is on the Earth. There's a variable flux. I'm not going to repeat all the numbers on the graph there, but basically the smaller the object, the more there are of them. A lot of surface rocks have craters that are on the order of 1 to 10 microns. That's the size of the crater. In many cases, the damage from the impact extends far away from that actual crater, and it creates something we call zap pits. The Apollo astronauts noticed zap pits on the surface rocks, and once the rocks were back, it turns out that it becomes a very useful piece of data as to how long a rock's been sitting on the lunar surface and whether it's been tumbled. In other words, does it have the same face always facing the sky, or has it been rolled around? If it hasn't been tumbled, the top surface will have a lot of zap pits, the undersurface won't. If it's been tumbled around, the undersurface will have zap pits. And it turned out we could actually determine how rocks were bouncing around on the lunar surface by looking at the zap pits. One critical part of the discussion of micrometeorites is that even though there's micrometeorites coming into the moon and they're not slowed down, the impact hazard on the lunar surface is estimated to be about 4 times less than in low Earth orbit. So the lunar surface environment is much safer in terms of micrometeorites than low Earth orbit, where International Space Station is. Now, the moon's orbit is pretty interesting. Like all bodies in the solar system, it's not in a circular orbit, it's in an elliptical orbit. And in this case, the perigee and apogee being the farthest it's away from the Earth and the perigee being the closest it is, vary by about 45,000 kilometers. One key part of the fact that the moon has an apogee and perigee is that the size of the moon is actually quite a bit different when it's as far away as it can get and as close as it can get. The one on the left is when the moon is as far away as it is from the Earth. The one on the right is its closest approach. And there is a considerable difference in the moon's size. So when you step out at night and look at a full moon and you think, gosh, that's a lot larger than I remember it being, sometime in the past, it's not an optical illusion. That's actually happening, and it's because the moon is in an elliptical orbit. There's something we call the barycenter, and that is the center, the point at which the entire system rotates, and that's about 1,700 kilometers below the Earth's surface. It is not at the center of the Earth.